Welcome back to Atomic Theory. In part 3 of this unit, we're going to be talking about waves in the electromagnetic spectrum, which will lead us into photoelectric effect, and finally a couple of models of the atom, solar system model, shell model, and photoelectron spectroscopy. Let's go. So first of all, we need to understand just a little bit about waves and wavelengths and frequencies so that we can figure out how electrons move. So first we've got wavelengths. That's the distance between the crests of a wave. So if we're looking at this picture down here in the bottom, the crests are the top, or the peaks of the wave. So the distance between two crests of a wave is the wavelength. You can also think of the distance between two troughs of a wave as the wavelength. Those should be the same distance. So that's our wavelength. It's represented by the Greek symbol lambda, and the units are going to be centimeters or nanometers. Then we have frequency. That's the number of waves that travel across a given point in a given time. So this would be, notice this wave, there's a lot of waves, 1, 2, 3, 4 waves in a particular amount of time. And in this low frequency wave, there's only 2 waves that travel across a given point in a given time. So the units of this are going to be per second, as in waves per second, or hertz. And a hertz and a per second are the exact same thing. So a hertz is just how many waves per second. So hopefully you can see the longer the wavelength, the fewer waves can pass by in a given time, so the lower the frequency. So if I have a really wide wave, then I can only have maybe 1, 2 total waves in a particular time. Whereas if I have a really short wave in the same distance, I can have 1, 2, 3, 4, 5. So wavelength and frequency are inversely proportional. Now all electromagnetic radiation, this is microwaves and X-rays and gamma rays and light, all travel at the exact same speed, which we call the speed of light, which is 3.0 times 10 to the 8 meters per second. So the formula to relate speed or velocity, frequency, and wavelength, the speed is equal to the wavelength times the frequency, which shows that wavelength and frequency are inversely proportional. If frequency goes up, wavelength will go down so that they can multiply to equal the same constant, and vice versa. So we can use that formula to find the frequency of green light that has a wavelength of 545 nanometers. So first of all, 545 nanometers and 3.0 times 10 to the 8 meters do not have the same unit of distance. So my very first step is factor label, going back to unit 1 and looking to see how many nanometers there are in a meter. So 545 nanometers. Nanometers to meters. A meter is larger than a nanometer, and referencing my notes from unit 1, 1 times 10 to the 9 nanometers in a meter. So if we divide that, we end up with 5.45 times 10 to the negative 7 meters. The reason why I'm doing that is so that it will cancel with a unit for speed. So we can rearrange this equation to find frequency. That would be speed of light over wavelength. By the way, that's the Greek letter lambda, not a V. It's the Greek letter lambda. So I'm going to take frequency is equal to speed of light, 3.0 times 10 to the 8 meters per second, divided by wavelength, which we just calculated as 5.45 times 10 to the negative 7 meters. And now the meters will cancel. So we end up with 5.5 times 10 to the 14 per second, or 5.5 times 10 to the times 10 to the 14 hertz. And that is the frequency of this green light. So the electromagnetic spectrum will actually show the range of all possible frequencies of electromagnetic radiation. Remember that all of these different types of radiation travel at the exact same speed. So radio waves travel at the exact same speed as X-rays or gamma rays, which might even turn you into Spider-Man. And notice that visible light is there in the center. Visible light has a very small range, but within that small range we get all of the colors of the rainbow. So longer wavelength towards the left, shorter wavelength towards the right, greater frequency towards the right, shorter frequency towards the left. So it's important here to note that there is a wave-particle duality of light and electrons. So from experiments, we know that light travels like a wave. It has a wavelength and has a frequency. There's actually a really famous dual slit experiment that I suggest you look up to show how light travels like a wave. But what's interesting is that light also acts like a particle. Einstein proposed this with the photoelectric effect, that light actually has mass and can travel like an individual thing rather than just a wave. Well, it turns out that electrons are the same way. Electrons act like waves and particles. And this doesn't mean that it acts like a wave one second and a particle the next, but it acts like a wave and a particle at the exact same time. So it has mass and travels, like, say, like a baseball thrown through the air. But it also travels in waves like a light wave. So all of our experiments on light lead us to experiments on electrons, which lead us to understanding how electrons act outside an atom. So now back to the atom. Max Planck stated in 1900 that there is a minimum amount of energy that can be gained or lost by an atom, and all energy gained or lost must be some integer multiple of that minimum. So classical physics, like Newton physics, stated that any energy could be possible. So we could have energy anywhere along this line. But Planck proposed that only certain energies are possible. The magnitude of the quantum of energy depends on the frequency of the radiation. So my electron or atom can give off this much energy, or this much energy, or this much energy, but it can't give off any of these amount of energies in between. So this would be like Newton says, if you want to get from point A to point B, you can stop anywhere along the way. You can take 10 steps along the path, or a half a step along the path, or you could just move a little baby inch, and that's totally all right. You can stop anywhere from point A to point B. Whereas Planck sees it more like a staircase. You can stop at the bottom stair, or the first stair, or the second stair, but there's no way to step on half a stair. You can't hover in between two stairs. So Planck says that there are particular amounts of energy that an atom can have, and if there's particular amounts of energy that an atom can have, that might mean there's particular energy levels outside an atom. So Planck gave us an equation that directly relates energy and frequency. And so energy is equal to H, which is Planck's constant, 6.626 times 10 to the negative 34 joule seconds, times frequency. So if energy increases, then frequency increases, and vice versa. So now we're going to talk about the photoelectric effect. The photoelectric effect occurs when light bombards the surface of a metal and electrons are ejected. This would be as if you turn on an electric stove and the coils get red. The coils are getting red because electrons are being ejected, and we're seeing those electrons as light. So let's say you shine a flashlight onto a piece of metal, and then notice this has a very low frequency. There's not very wavy light. So when I shine light of low frequency, even if I shine 2 flashlights worth of light of low frequency onto this metal, the electrons are not going to be ejected, no matter the intensity of the light. When the frequency is too low, electrons will not be ejected, no matter the intensity. So it doesn't matter if I shine 1 flashlight worth of light or 2 flashlights worth of light. If it's a relatively low frequency light, then no electrons will be ejected. At a certain frequency, however, when the light becomes a certain frequency, electrons begin to be ejected when that light hits the metal. So if I had 2 flashlights worth of light, or I increased the intensity at the same frequency, notice I'm going to get more electrons being ejected, but they all have the same speed. None of them are going any faster than any of the others. At a certain frequency, electrons begin to be emitted. Increased intensity increases number of electrons, but not their speed. So after that point, after that increased frequency, if we increase frequency even more, I'm going to get the same number of electrons ejected, but now they're going to have greater speed, represented by these greater arrows. So increased intensity will increase the amount of electrons, but not the speed. Increased frequency will increase speed. The increased frequency above the threshold increases the velocity of electrons. All electrons share the same velocity. And that is called the photoelectric effect. So Einstein studied the photoelectric effect, and one quick note, Einstein was born in Germany but renounced his German citizenship at the beginning of World War II. He's actually a man of many countries, at the end of his life even America. So, just a side note. So Einstein studied the photoelectric effect and realized that electromagnetic radiation is quantized, which means it can come in particular amounts and can be viewed as a stream of particles called photons. So a photon is pretty much a particle of light. Earlier we said that light can act like a wave, but it can also act like a particle. So a particle of light is called a photon. So the energy in E equals h, or h times frequency, is the energy of a photon, or a particle of light. So using the theory of relativity, E equals mc squared, and E equals hv, or h frequency, the mass of a photon can be calculated. So let's do that really fast. Mc squared is equal to h times frequency. And since frequency itself is c over wavelength, then mc squared equals hc over wavelength. We can cancel out a c on both sides, so we end up with mc equals h over wavelength. If we divide both sides by c, we'll get m equals h over wavelength c. You are not responsible for the derivation of that formula, but I think it's kind of interesting just to see how it works. So all of this information was put together by Niels Bohr, who is from Denmark, and he proposed the solar system model of the atom, where electrons move around the nucleus in circular orbits, such as the nucleus is the sun and the electrons are orbiting like planets around. He said that only certain orbits are allowed, and each orbit is a fixed distance from the nucleus, so just like a planetary orbit. This is also called the shell model, so there's several energy levels or shells outside the nucleus. He says that an electron within an orbit has a set quantized energy level, the energy can't change, and this accounts for the line spectra produced instead of a continuous spectra. So this is about if you took hydrogen and shined electricity through it, so hydrogen gas, then that hydrogen would produce light. If you took that light and put it through a prism, you would see a individual few lines of color, not a continuous spectrum of color. So if you used prism paper, you would not see a continuous range of color, just an individual few lines of color. This led Bohr to believe that there are individual places where the electrons can be, since there's only individual colors given off when you shine that light through a prism. So he says electrons are orbiting at a particular level, and the nucleus is on the inside. So if there are particular orbits outside the nucleus where the electrons can exist, then there also must be a shielding effect. The shielding effect says that electrons furthest from the nucleus are partly shielded from the nucleus by the electrons in the inner energy levels. So if we want to know how much shielding is going on, if we try to remove electrons, individual electrons, then we can see how much energy it takes to remove those electrons, and therefore how much the outer electrons are being shielded from the nucleus by the inner electrons. That's what the first ionization energy. It's the minimum amount of energy required to remove the outermost electron. From an atom. It always requires energy to remove an electron from an atom, so therefore the removal of an electron is an endothermic process, and ionization energy values are always positive, because it always requires energy to remove an electron. So this would be something like sodium. If you remove an electron from sodium, then what's left is Na+, or fluorine. If you remove an electron from fluorine, then what's left is F+. And if that bottom equation looks wrong to you, it's because it requires a significant amount of energy to remove an electron from fluorine, and it's not very likely to happen. This first graph shows how much energy is required to remove the first outermost electron from these particular elements. So let's say hydrogen requires this particular amount of energy to remove its one electron. Helium requires more energy than that. Lithium requires much, much less. We'll get to why in just a second. So notice as you go across a period, say from lithium to neon, ionization energy increases, but as you jump down a group, ionization energy strongly decreases. And then going across a period again, it increases again, and going down a group, it decreases again. So if it increases going across this way and decreases going down, then overall, say helium, or the top right-hand corner of the periodic table, should have the highest first ionization energy, and the bottom lower left should have the lowest first ionization energy. So let me point out a couple of things from that ionization energy chart that we were just looking at. Say, the difference between the first ionization energy of hydrogen and helium. Helium is almost double hydrogen. Helium has an ionization energy of about 2,300 kilojoules per mole, and hydrogen's about 1,300 kilojoules per mole. So why does helium take so much more energy to remove an electron than hydrogen does? And maybe it's because helium has twice as many electrons and protons as hydrogen does. So hydrogen has one electron on the outside and one proton on the inside. So removing it takes much less energy than two electrons and two protons. We're going to use that from Coulomb's law. Remember earlier, Coulomb's law, the force or the energy required, a constant Q1, Q2 over d squared. And d squared is the distance, and Q1 and Q2 have to do with the charges of the nucleus, the positive protons, and the charges of the negative electrons. So if I have a greater quantity of charge, greater protons, greater number of electrons, then that will account for the difference in helium versus hydrogen. Since they have the same distance, what you're dividing it by won't even matter at all. So this guy is the same, and this is double. Which is totally fine until you look at hydrogen and lithium, because it seems like lithium has 3 electrons and 3 protons, and hydrogen has only 1. 1 electron and 1 proton. So using the same logic we did with hydrogen versus helium, it seems like lithium should have a whole lot more of a first ionization energy than hydrogen does, because now there's even more electrons and protons. But in fact, hydrogen we said was 1,300. Lithium is only about 530. It's less than half of hydrogen. And so that must mean that in that same Coulomb's law, even though Q1 and Q2 are much larger, the distance must also be much larger, and when we're dividing by a larger distance, that's going to end up with a lower force, which tells me that the outermost electron that you're trying to remove for the first ionization energy in lithium must be much further from the nucleus than the outermost electron in hydrogen. So maybe this means, in Bohr's shell model, that that outermost electron in lithium is actually in a further energy level. So maybe this is hydrogen and helium, and possibly lithium is an even further energy level, so it requires less energy to remove because of the shielding effect. And actually, using this logic, we can tell that the n equals 1, or the first energy level, can only hold 2 electrons, because after the first 2, the first ionization energy drops dramatically. And so then, the second energy level must hold 8, because after the next 8, the energy required drops dramatically. And so then on the n equals 3 shell, it can hold 18, because after the next 18, the amount of energy required drops dramatically. And in this way, we can see how many electrons are in each energy level. Electrons in the inner shells are called core electrons. Electrons in the outermost shell are called valence electrons. You do need to be familiar with those terms. So the problem is the anomalies within the first ionization energy, from beryllium to boron and from magnesium to aluminum. So we're going to use photoelectron spectroscopy to help explain this. So photoelectron spectroscopy is a process by which high-energy photons can remove any electron throughout the atom, not just from the outer shell. Once the electrons were ejected, the frequency is recorded and the kinetic energy can be determined, and then using these calculations, we can decide the first ionization energy for any electron. So here's an example of a graph produced by photoelectron spectroscopy, and actually this is 5 different graphs. We have hydrogen and also helium and also lithium. So we've combined 5 different elements, PES graphs, onto one big chart so we can kind of compare them. So notice the axis for relative number of electrons relates to these peaks. So the first peak, the only one peak in hydrogen, is about half as tall as the one peak in helium, which tells me that hydrogen has half the number of electrons. And so we're going to say 1 electron for hydrogen, 2 electrons for helium. Notice that in lithium, it has a peak that's a relative height of 2, but there's an additional peak with a relative height of 1. So there's 2 electrons over here to the left, and only 1 electron for lithium. So if we go down to beryllium, both of the peaks have a relative height of 2, which is a total of 4 electrons. And then to boron, we have 2, 4, 5, so 5 total electrons. Okay, now let's talk about the energy itself. Over here, notice that ionization energy actually increases as you go more to the left. So if we were looking at the peaks for lithium, it requires more energy to remove these 2 electrons, 6.26 megajoules per mole, than it does to remove this 1 electron, 0.52 megajoules per mole. Which tells me that the 2 electrons on the left must be the core electrons, because it takes much more energy to remove them. They must be closer to the nucleus. And the 1 electron on the right must be a valence electron. This lends credence to our idea of the shell model of outer energy levels. So if we say in beryllium, those 2 electrons are core electrons, then these 2 electrons must be valence electrons. And then again for boron, 2 core electrons and 3 valence electrons. Now, it's a little bit odd that those 3 valence electrons have 2 separate peaks, and they're not 3 in 1 peak. Let's look at a couple more examples before we talk about why. So here's the PES graphs for the next 5 elements, carbon all the way through neon. And notice that they all have, at least on the carbon, they all have the same relative height. And if you compare that to the other graph from the slide before, those are all a relative height of 2. So they have 2 electrons on the left, 2 electrons in each of the peaks on the right. And then we can say that these 2 electrons on the furthest on the left must be the core electrons, and these 4 electrons must be the valence electrons. So then if we look at nitrogen, we have 2 core electrons, and then for our valence electrons, this has a relative height of 2, and this one comes about half the height of the one from above it, so I'm going to say that's 3. So we have 5 valence electrons. Then if we look down at oxygen, again we have the 2 core electrons just like we did before. Now we have a peak with a relative height of 2, and a peak which looks like it goes twice as high, so that's a height of 4. So this would be 6 valence electrons. And then if we move down to fluorine, we have our inner peak with 2 and then another 2, and this one looks like it goes to about a height of 5, so there's 7 valence electrons, and neon has 2, 2, and this one goes triple high, so that would be 8 valence electrons. Okay, so why on these valence electrons are there 2 peaks and not just 1? If all of these are in the second energy level, EL for energy level, and all of these core electrons are in the first energy level, then it seems like all the second energy level electrons should have the same amount of energy to remove, but there's not. There's different peaks within the second energy level, which must mean that there's something going on within the second energy level, maybe just not a full energy level, but possible sublevels. So now we're going to take Bohr's model of the atom and refine it even further. I hope you join me again next time for the quantum mechanical model. See you then.